Hello. So, are we live actually? Yeah, looks like we are. So I've got like 5 hours of time free, and I can just go on and on endlessly. So, yeah, just wait a second, let me check a few things. Yeah, looks good. So, in short, what I'll be doing now is that I'll be basically looking at the things which we have discussed before already, like the fundamental groupoid and the fundamental group and the functors, going here and there and calm down a bit and look at them a bit through a bit more careful eyes. And yeah, that is it. This will be a very slow one. There will be lots of probably silent moments where nothing is going on. Yeah, I might play some music. The last time I played some music, it got copyright claimed because I'm an idiot. But um, I'll look for some copyright free music. I just have to check a bit. I do have some stuff which is very clearly copyright free, but I'm not really sure if I should use them or not because just the music might not be very suitable. Let me just see. So it's just Bach after all. I'll avoid Glenn Gould's recordings because they're almost all very tightly knit by the copyright system. Might try some of this. Yeah, this should be good to go. Yeah. So the last time it was Goldberg variations as well. So yeah, let's go. Okay. Let's just get this down first. What the books are talking about. What the books are talking about is, let's first see Moncrief this time, not Hatcher. So Moncrief first talks about homotopy of paths. So he defines what the homotopy of maps is. Then for any initial point and any final point, x0 and x1, he defines what a path is. Then he defines what it means for two paths to be homotopic and shows that these two relations, the homotopy of maps and homotopy of paths, are equivalent. Remember that there is a slight extra condition for homotopy of paths, in that which requires the endpoints of the path to be always fixed during the homotopy, which is not exactly required for a general homotopy of maps. Although one could view homotopy of paths as being just homotopy of map, where the map is from the interval I or close 0, 1, but there is that extra condition which makes it slightly different than that. Okay, then there goes the lemma. There's some examples. Any two maps in R2, any two paths in R2 They are homotopic by the map. This is just connecting them, interpolating them by the what is that called? The Jensen term, which is like 1 minus t times f of x plus t times g of x. So it starts at f of x and gradually, as t increases, it just moves to g of x. So there is that. This is called the straight line homotopy because it is the straight line. It is the straight line connecting them. 1 minus t times f of x and t times g of x. So it is the straight line connecting f of x and g of x. There's that. More generally, let A be any convex subspace of Rn, which means basically that any line connecting any 2 points inside that subspace, or rather subspace of Rn as in like a topological subspace, not linear subspace, any convex set of in Rn where the line connecting any 2 points in the space in the set also is entirely contained in the set, so that no chords get outside of the set. You cannot move outside the set by connecting chords. So that is what convex set is. Then any two paths f and g in A from x to x naught are homotopic in A. That is because you can just do the straight line homotopy and it would be a homotopy inside that set, that convex set in Rn. Okay. And then there is an example of the punctured plane, which is basically homotopic to a circle. So I'll introduce some algebra into the geometric situation. We define a certain operation on path homotopy classes as follows. So yeah, this defines a star product of two maps or star composition. Although I do not really like the fact that the star is written as f star g, whereas it actually should be written as g star f. So there's that, or maybe I'm just writing the entire thing in reverse or something like that. Okay, yeah, this is a good point to follow up on actually. So okay, so as it turns out, in the last stream the notation I used was complete bogus. What was the notation I even used? Should be somewhere here. Yeah, I did this in order to denote, first you go f and then you come back f dash. I denoted this. I reckon it does not make much difference. But yeah, this makes sense. This makes sense. It is not a problem because we are looking at these maps as being these things P and Q as being morphisms in the category. Which category, by the way? I guess yeah, the category, the fundamental groupoid. Since P and Q are morphisms in the fundamental groupoid, I reckon that yeah, that notation is fine. It is fine. It just differs from the conventional notation of the other books, where they go like f star g, which is defined at the point t as being f of 2t if t is less than or equal to half, and g of 2t minus 1 if t is greater than or equal to half. And that is the same thing which I denoted as being g star f. That is because if the homotopy class of f, let's say this is denoted by p, and the homotopy class of G, or rather the path homotopy class of G, is be denoted by Q. Then these are morphisms between the objects of the fundamental groupoid, which are basically the points in the space. And since morphism composition has a particular way of writing them, I would prefer to write it in this form, which basically makes it look like let's say this. Not really. Not really. Which makes it look like this. And if you just do that thing which everyone does, making it look like a homomorphism where it is not, then you get it is actually it should look like G star F. Although you could completely alternatively define, like, this star does not exist, right? Because it's just morphism composition, so you can just put a composition in there or just put nothing. It is how it is what it is. You could completely define that thing to be just F star G, where you use F star G, the notation for just maps. So it is completely up to who is doing what, and just make sure to always give the definition of exactly which notation you are using. I guess up till then we'll be doing fine. So there goes the homotopy. Yeah, okay. There goes associativity. The proof is ginormous, first of all. First up, the proof is absolutely ginormous. That is because, Moncrief works out all the details, which one actually has to, because there's no other way around. You have to work out all the details. But should we look at the proof? Would it be worth it? Not really sure about that. I guess it could be worth it. But okay, let's look forward to what else is there. Then we'll see. When James or Moncrief is talking about terminology and what terminology he's using in midst of a proof, there's something fishy going on right there. It's a bit sketchy. Let f be a path in X, and let a0 a up to an be numbers such that they're in increasing order, and a0 is equal to 0 and an is equal to 1. Let fi from I to X be the path that equals a positive linear map of I onto ai minus 1 comma ai followed by f. Jesus Christ, what was that? Okay, so the terminology entirely comes from the previous proof. Positive linear maps have not been defined previously, so I guess we'll have to look at the proof after all. Yeah, I'll just at least read the proof and see what's going on. Okay, so then it brings the fundamental group in question. The set of path homotopy classes of a space does not form a group under the operation star because the product of two path homotopy classes is not well defined. But suppose we pick out a point x0 to serve as a base point and restrict ourselves to those paths which begin and end at x0. The set of these path homotopy classes does form a group under star under the path composition operation, or the class composition, whatever. This will be defined as the fundamental group. Then he reviews some of the group theory stuff, homomorphism kernels. Actually, I'll be back in a few minutes. So, I guess we are back. Okay, then Moncrief then talks about the group stuff, homomorphism, what is a kernel, monomorphisms, epimorphisms, isomorphisms, normal subgroup, cosets, quotient. Okay. Then he just slightly defines what a loop is, defines the fundamental group. Sometimes this group is called the first homotopy group of X, which term implies that there is a second homotopy group. There are indeed groups pi n of x, x naught for all n in Z, but we shall not study them in this book. They're part of the general subject called homotopy theory. Okay, I'll be very happy to look at homotopy theory because I'm loving this. I'm completely loving this. So, okay. Definition: let alpha be a path in X from x0 to x1. We define the map alpha cap from pi 1 from the fundamental group based at x0 to the fundamental group based at x1. So, okay, yeah, that makes complete sense. So this exactly defines something like this. You have a loop at x0. Let's say this is alpha, this loop is f. Then you go from x1 to x0 via alpha bar. Then you do f, then you come back through alpha, and that gives you a loop at x0 at x1, which is in the notation of Moncrief, alpha bar f alpha. So there's that. The map alpha hat is well defined because the operation start is well defined. If f is a loop based at x0, okay, so this map alpha hat of this not actually of this map, actually of this class f, is defined to be exactly that thing, alpha bar f alpha. Hence alpha hat maps pi 1 of x, x0 into pi 1 of x, x1 as desired. Note that it depends only on path homotopy class of alpha. So actually this is just conjugation by alpha. This is basically alpha inverse f, or like conjugation by alpha inverse if you want to look at that way. But this actually, like for map composition, this is supposed to be written like this. So yeah, it is actually conjugation. Show that the map alpha cap is a group isomorphism. Yeah, just like all it is an isomorphism, just like all conjugations are. All conjugations give rise to isomorphism. In this case this is slightly more interesting because the conjugation is not taking place by some element of the group. It is taking place by some element of the groupoid. So suppose here is that object x1, here is the object x0, not just necessarily the points in the space. We are talking about the inside the category fundamental groupoid of x. So there's this map alpha, and of course there is this map alpha inverse, and there's this loop F. So yeah, this basically translates into something based on, actually I did it in reverse kind of. So this translates into this, a map at x1, which is being called alpha hat of f, or since we are taking f to be the morphism here, we can just say it is the alpha hat of f. So it is just composition like this. It goes like this. You start here, go by that, take that route and come here. That is a loop, right? So that loop is exactly, you first do alpha inverse, then you do f, then you do alpha. So that is a conjugation action. I guess conjugation in groupoids give group homomorphism. I'll just look that up a bit because this certainly seems interesting. Oh, there's a math stack exchange post called conjugation in a groupoid. Exactly, it is called exactly that. In a group G, the conjugation of any element G and G by H defines an inner automorphism. So phi psi sub H is given by taking G to H inverse. If one consider instead a connected groupoid, he just named it a square for some reason. Connected groupoid, a box. Is there a similar definition of conjugation of the morphisms of square by a particular morphism mu h in square? The correct analog is the following one. Each object x of your groupoid, for each object x of your groupoid, choose an element mu x in hom x comma x, call this the entire construct mu. You can now define a conjugation by mu by mapping them. You know what, I'll just actually show this. X is a topological space. Let's see with the path component of X. X is containing actions. Give Okay, so I wrote all this stuff, and all that was showing up was the Stack Exchange page. Okay, fine. Stack Exchange is good. I just hope I don't get copyright striked like on this stream, because I don't think this recording, you can even download this recording on YouTube, so I guess this is copyright free. But okay, let's go. Let's at least let's credit the player. It is Jean Rondeau playing the Bach Goldberg variations. So there's that. Listen to more of Jean Rondeau's recordings. They are absolutely fabulous. Fundamental group of the circle, covering spaces, blah blah blah. I'm not looking at that right now. Oh, let's see what Hatch has got to say. The more I read Moncrief's book, the more I love it. It is such an absolute brilliance. Path and homotopy, paths and homotopy, linear homotopy, product path, composition of paths, inverse path, simply connected spaces. Space X is simply connected if and only if there is a unique homotopy class of paths connecting any 2 points. Yeah, that's good. What is the next variation? You just stopped and This man is such an absolute genius. But then Hatcher directly just jumps into covering spaces in the fundamental group of the circle. So I guess he covers less than Moncrief does. It's just like 3-4 pages. Then all those application things, Bauer fixed point theorem, fundamental theorem of algebra, and Bose-Ulam theorem for S2, induced homomorphism. Then he talks about the induced homomorphism, a little bit of functoriality. Okay, the first of these follows from the fact. Okay, so suppose phi from x to y is a map taking the base point x naught to the base point y naught. For brevity, we write phi from x comma x naught to y comma y naught. In this situation, phi induces a homomorphism phi star from pi 1 of x comma x naught to pi 1 of y comma y naught, defined by composing loops, blah blah blah. Two basic properties of these induced homomorphisms are that there are no homomorphisms, and there's the star is a homomorphism of homomorphisms, and that one star is the one. So the identity map induces the identity homomorphism. The first of these is follows from the fact that composition of maps is associative. Okay, the second is obvious. These two properties are induced homomorphisms, or what makes the fundamental group functor. The formal definition of a functor requires the introduction of certain preliminary concepts like categories. However, we postpone these until it is needed in 2.3. So we actually talk about categories in 2. Whatever computations and applications. So this is homology, and I have absolute zero clue what homology is about, but I'll try and eventually get to it. It looks like there's a lot of cell complexes going on. Meyer-Vietoris sequences, homology coefficients, exercises. Then we get lots and lots of exercises. They're like 43 problems. A formal viewpoint. Nice. Axioms of homology theory, categories and functors. Nice. He does talk about categories and functors. Functor, covariant, contravariant, number of these constructions. Okay, nice. That looks absolutely gorgeous. Homology and the fundamental group, and lots of holes, classical applications. Okay, is that the Horned sphere? Alexander Horned sphere. That is also another beast. The Bose-Ulam theorem, cyclical approximations and stuff like that. Yeah, absolute gorgeous stuff. I must get to it someday. Homology, cohomology. I just have a sneak at the last chapter, which is called homotopy theory. I guess it should be approachable after knowing a bit of homotopy. If it's not, then I can just flip back the pages. Homotopy theory. What does it say? Homotopy theory begins with the homotopy groups pi n of x, which are the natural higher dimensional analogues of the fundamental group. These are higher homotopy groups. These higher homotopy groups have certain formal similarities with homology groups. For example, pi n of x turns out to be always abelian for n greater than or equal to 2. What? Homotopy groups are all abelian other than the fundamental. Damn. Other than the fundamental group, all homotopy groups are abelian. And there are relative homotopy groups fitting into a long exact sequence, just like the long exact sequence of homology groups, whatever that means. However, the high homotopy groups are much harder to compute than either homology groups or the fundamental group, due to the fact that neither the excision property of homology for homology nor the Van Kampen's theorem for pi 1 holds for higher homotopy groups. Okay, so Van Kampen is just for pi 1. Okay, sure, why not? He talks a lot about these things. He just gives the sphere chart, but you can see Wikipedia. Okay, suddenly sounds very saucy. Whitehead's theorem, cellular approximation, CW approximation, Postnikov towers, Whitehead towers, elementary methods of calculation, excision for homotopy groups. Okay, excision is apparently something which is okay, so this does not look very approachable. I'll not look at it anymore because I'll just stick to doing what I should be doing. Applications with cell complexes, free products of groups. Okay, then there's Van Kampen's theorem. What is there after that? Okay, so Cayley, not Cayley diagrams. Covering space. Lifting properties, yay! Lifting properties. Okay. Quasi-circle, topology, sine curve. Great. Graphs and free groups. Every subgroup of a free group is free. KG, 1 spacious. Okay, that's a lot of stuff. That's a whole lot of stuff. Oh, okay. So that is the first part of the stream, which is called just getting started. I bet that it was almost an hour. Yeah, 40. That was more than 46 minutes of streaming just to, get the bearings right and get started and all that. How long has this been going on even? Almost 50 minutes. Sure, why not? When you got 5 hours, you gotta use the 5 hours. It is 4:22 a.m. right now. And I've got at least I can see at least 4 more hours. So yeah, I'm not in a hurry. Inner automorphisms for groupoids. Yeah, let's just start by doing inner automorphisms for groupoids. I just realized that I should probably turn this on. So what do the inner automorphisms for groupoids look like? So that is what a groupoid is, right? A groupoid has objects, and only morphisms are isomorphisms. Okay. Let X be an object of this groupoid. Okay, then out of X, I'm just omitting the name of the groupoid and all that, because we are talking about a groupoid, right? A particular groupoid. And out of X is also just the same thing as end of X. So the only morphisms are automorphisms, isomorphisms. So the endomorphisms are all automorphisms. Is a group similarly out of Y is also a group for Y object. Now, if it turns out that there are morphisms between X and Y, if there is, let's say, F from X to Y, then check this out. Then we can say that the automorphisms of Y can be given by the following set, which is F, G, F inverse. Yeah, so it just looks like that. F, G, F inverse, such that G is in automorphisms of X. Yeah, so what you can do is say that, call this, just be sloppy and call this F out of X F inverse, so that you can call it. And similarly, out of X is isomorphic to out of Y. Then that is because we just need to show that this conjugation, this what do we call this even? Let's call this kappa for the lack of a better name. Kappa sub F of kappa sub F is an isomorphism You hear those? Those are peacocks just yelling. Kappa sub f is an isomorphism. So this is something we have to prove right now. Let's just prove it then. Kappa sub f is an isomorphism. Okay, how does one prove it? Just show it is injective and surjective. That is enough. Or is it? How do you show that something is an isomorphism? We show that there is an inverse isomorphism. Okay, so this is probably better, or no, matches my style more. Produce. Okay, first of all, kappa is in homomorphism, right? Kappa sub f is indeed in the is indeed an element of this. Out of where to where actually? Out of x to out of y. We produce an inverse of kappa f in this. So this is we pick an homomorphism, pick a homomorphism from the automorphisms of y to the automorphisms of x, and we produced an inverse of kappa. So let's just define kappa inverse, kappa of f inverse Isn't this variation absolutely beautiful? Oh, I forgot to turn on the charging and all this stuff. So, yeah. This is great. We just define it to be that. And just as a reminder, this guy takes some, let's see, G and maps it to F inverse GF. So this G is in automorphism of Y, this is in automorphism of X. Kappa F is in homomorphism from out X to out Y. That it is because kappa of G, or rather kappa of F2, kappa of F1. If we compose those two maps, let's add G. Well, now there's an issue right there. Oh, not actually, I'm doing the wrong thing. Kappa F of G1 G2, that is equal to F G1 G2 F inverse, and is equal to F G1 F inverse F G2 F inverse, therefore equal to kappa F of G1 kappa F of G2. So we see that we have an inverse here. Also just just put it like this: kappa F inverse on kappa F, that's G, that would be kappa F of this F inverse G F, that would be F inverse G F inverse, that is just G. So kappa F inverse is the identity on out of Y, I think. Here is out of Y. Kappa F inverse kappa F of G. Similarly, you just change the roles, so it is kappa F inverse of F G F inverse. So this is F inverse F G F inverse F, that's just G. So okay, I guess I'm just being too lazy here. This G is in out Y, this G is in out X. I should be really using different notations for them, but yeah, who cares, as long as it's all understandable. Yeah, the dot of the I got missing. I just realized that there's this idiom dotting one's I's and crossing one's T's. So yeah, I just dotted the I and crossed my T. Anyway, that's fine. So that is an inner isomorphism of the groupoid. Not really an inner isomorphism of a groupoid. That's wrong to say, because for a given F, you can only give an isomorphism between just the two groups, between the automorphism groups of the two objects. But yeah, still. Damn. 2019 was 6 years ago. All of that 2020 happened 5 years ago. Okay. Okay, what we doing next? Up next, simply connected space and pi1. So in short, if a space x, if a space x as being a space in, let's say, top is path connected, then uh, then all objects of pi1 of x are isomorphic so this is one thing to show, which we can show as follows. We can just say that if x is path connected, then consider any x and y being objects of pi1 of x, or you can just let them be points in x, same thing. So they're just objects of pi1 of x, and I'm being lazy and denoting them as being elements of pi1 of x, where pi1 of x cannot really have elements and as such. But yeah, anyway, foundational issues aside, as Ravi Vakil said, you don't really want to live your life like that. So okay, you can only care so much about foundational issues. Consider any two objects. Since there is a path between x and y as they are objects of x, we know that there is a morphism f of pi1 of x from x to y, since pi1 is a groupoid, f is an isomorphism. We have seen all of this in the previous stream. So x is isomorphic to y, and each path component we see this as kind of a corollary, that each path component of a space gives a, and let's put it that way, and isomorphism class of pi1 of x. So in some sense, the x by this being path connection, this is really the same as this, Yeah. And if you consider this quotient space, actually, so x quotient by path components, so basically path components of x, or you can just choose to call them x p or something like that, whatever. um, this quotient space, what would be the morphisms as such? There are not really morphisms, because there are no morphisms between components in x as such. So yeah, this thing, since this is a category in of itself, you take a quotient of it, that should be also be a category. This is a discrete category. And that is only true because and only because pi n of x is a groupoid. If it was not a groupoid, then suppose there are some isomorphism classes here, there are some isomorphism classes here, there would be just usual non-isomorphism morphisms between these. So it's but since it is a groupoid, and these morphisms do not really exist, you can say that only these identities exist as such. So there is that. But this is when the space X is path connected. And there's another notion, which is simply connectedness, or simple connectedness, whatever. X is simply connected. This is Moncrief's definition. If X is path connected and that thing which is the fundamental group is trivial for some base point. I guess this ended. Okay, yeah, I cannot just start with Glenn Gould. Let's put this on loop. Let's loop this. Can I not even loop this? Come on. That's just so sick. This is so completely sick. Why cannot I loop this? Les variations Goldberg. I don't want to continue with this playlist. Come on. Anyway, that aside. A space is simply connected if it is path connected and the fundamental group is trivial for a base point. That is to say, I will just take this part literally for some base point, and hence this happens, that follows naturally. So first of all, if X is simply connected, then it is path connected. So the pi1, the fundamental groupoid of X, has all objects isomorphic. Right? The fundamental group of some at some base point which is just the same thing as automorphisms in pi1 of X at the base point x0. If that is trivial, then we see that then notice one thing, that the only automorphism is the identity. Okay, so the only automorphism is the identity. That means for some object y, consider maps x to y. Let's consider both f and g to be maps from x to y. So let's say here is x and here is y. Identity is the only map on x. Let's say here is the map f, here is the map g. We know since pi1 is a groupoid, there is this corresponding f inverse and there is this corresponding g inverse, right? And by composing this, we see that it's clearly okay. What did I do right there? That was not supposed to be it. There's this G inverse right here. And this is G. We see that G on F inverse. So F inverse G, that has to be the identity on X. And so has to be first F then J inverse. So that is FG inverse. So in the end, it says that F equals G is a morphism, right? So for all y in the fundamental groupoid being objects, there exists a unique object f sub y from y to x. This means x is a terminal object, terminal or final object. But similarly, you can just see that for all y in x, for y in the fundamental groupoid, there is just a unique f sub y from even x to y. So x is an initial object as well. But we know that for all x and y in the fundamental groupoid, we know that x is isomorphic to y. That is because there's this path connection property, right? So all objects are isomorphic. We know that. Therefore, all objects are both initial and final, and that is the distilled statement that we can make about x being simply connected. So x in top being simply connected, that corresponds uniquely with this fundamental groupoid. All objects, both initial and final. Yeah, so that is kind of it about path connectedness and simply connectedness. What else do we have? Isomorphism of pi1 x0, pi1 of x1 is independent of the chosen path if and only if both groups are abelian. Okay, that indeed is quite saucy. So the statement says that the isomorphism of the fundamental group based at x0 with the fundamental group based at x1 is independent of the choice of, there is exactly one isomorphism between these two spaces if and only if both of these fundamental groups are abelian. Okay. So let's write the statement. So there is only one isomorphism. Both of these groups are abelian. Yeah, I just noticed one thing a few days back, that people do not really capitalize the A for abelian. Why not capitalize the A in abelian? The A in abelian is not capitalized because it has become the standard mathematical term for commutative, making it more descriptive adjective than a proper noun. While it is derived from the name of mathematician Niels Heinrich Abel, its widespread use and generalization have led to the lowercase convention of mathematics, distinguishing it from the concepts that retain the capitalization. Euler's theorem, Gaussian integers, Noetherian rings. Okay. And abelian geometry written in lowercase. Okay, you guys cannot see this really. You have made it as a mathematician when they start using your name in lowercase. So so as it turns out, this word abelian, derived from Abel's name, has become like the staple of things becoming lowercase in mathematics. So this post in MathStack Exchange, this was asked 15 years ago. This is coming from 2010. My goodness. I would like to collect a list of mathematical concepts that have been named after mathematicians, which are now used in lowercase form, such as abelian. And they always give just one example, abelian. This question is partly motivated by my former supervisor, who joked something like, you have made it as a mathematician when they start using your name in lowercase. This is a community wiki. Please, one mathematician per answer. Please update already existing answer if the mathematician already exists. Please give a brief description of the concept of the person, blah blah blah. 14 answers. For something more common, Boolean. Yeah, Boolean. Damn, Boolean was also an example like that. Cartesian. Algorithm. Oh my goodness. Algorithm. Yes. Okay. So the thing is, the word algorithm comes from Al-Khwarizmi. Al-Khwarizmi. From Al-Khwarizmi's name, which this Kwa became more Gua, and so it became algorithm, and so it just became algorithm. This could be the this is probably the most mathematical word people use nowadays. I would say even more often than things like add, and I don't know. Add is probably the most mathematical word used currently. But yeah, the algorithm has become a super common word, and yeah, people don't even take notice of it. Yeah. Which letter of algorithm should be capitalized? That's a good question. Robin Chapman, 2010. Okay, so the thing is, Al Khwarizmi has this capitalization. If you had to follow that, your algorithm spelling would look like this: algorithm. And I mean, I don't really want to spell algorithm like that. Okay, I don't usually spell algorithm anyway. Okay, Cartesian. Cartesian. I was not really aware that Cartesian was commonly spelled in lowercase. But okay, Cartesian. Many things describe the Cartesian. When Descartes. It's weird that it is not more prevalent, given that Descartes is older than Abel by almost 200 years, and I can extend the Cartesian product and planes come at least as much as abelian groups. And the adjectival form of Descartes isn't just the name plus ending. It's strange how common the capitalized form has still remained. Yeah, it is actually rather weird, because if you look at it, Descartes' name. This is Descartes, right? They literally removed the day. They literally just removed the day and took the cart. Took the Cartes part. Just they took the Cartes part, and it became Cartesian. And they do not lowercase it that often. Whereas it is literally Abel is literally sitting here. This should be Abel N. Where it is not. They do not write it as Descartesian. They write it as freaking Cartesian. So I mean, there's that. I mean, okay, why am I even ranting about this? What we are supposed to do? Jacobian. I just saw Jacobian. I've seen Jacobian in lowercase for a few books. Are you kidding me? Noetherian rings? No way. No way Noetherian rings kept written in lowercase. No way. No way. Like, I'm not going around seeing Noetherian rings written like that. Come on, yaar. It is this. Or like, if you really want the anglicized spelling, yeah, just go with that. Noetherian. Probably this is the more common or more appropriate spelling. But to hell with appropriation. This is a perfectly beautiful way of writing her name. Just, perfect. 6 letters. Anyway, enough of that rant. Time to get back doing some maths, I guess. I actually do feel sleepy for some reason. it's surprising because I slept at around 10:30 or something like that, and then I just woke up at 2 a.m. and couldn't get any more sleep for some reason. I have absolutely no idea how, but somehow that happened. Then I made myself some food and ate and started this live. Yeah, it's going fine. I guess I'll prove this theorem and then look at some other stuff in the book. Did the light actually become dim? Don't really see that much light coming. I totally love this variation. Oh yeah, it actually did become dim. Okay, let's get to work and prove this. If there's only one isomorphism between pi1 at x0 and pi1 at y0, if and only if both groups are abelian. So both groups are abelian, huh? First of all, notice that there being only, or rather, let's just put it like that. The isomorphisms between pi1 of x and x0 and pi1 of x and x1 and GRP. So these isomorphisms are exactly in correspondence with isomorphisms, let's see, between x0 and x1 in pi1 of x. So we can safely change this condition to being exactly there is one isomorphism between x and x0 and x1 in the fundamental groupoid. That is probably a more natural way of looking at it. So here is x0, here is x0, here is x1. There's exactly one isomorphism this way, and there's exactly one isomorphism that way. This is f inverse. We have to show that these automorphism groups are abelian. So clearly if one is abelian then the other is also abelian. We have to show that it is abelian for somehow. Okay. There's something to think about. Is that exactly what was written in the book? Because that makes it looks like it is simply connected, right? I have to check it once again, I guess. Where was it exactly written, by the way? homomorphism induced. It turns out that the isomorphism of pi1 at x0 with pi so the isomorphism of the fundamental group at x0 and the fundamental group at x1 is independent of the path if and only if the fundamental group is abelian. This is a stringent requirement on the space X. So what is the exact previous paragraph? If X is path connected, then all groups pi1 of x comma x are isomorphic. So it is tempting to identify all these groups with one another and try to speak simply of the fundamental group of x of the space X without reference to the base point. The difficulty with this approach is that there is no natural way of identifying pi1 of x comma x0 with pi1 of x comma x1. Different paths alpha and beta from x0 to x1 may give rise to different isomorphisms between these groups. Okay. I might have to look this up a bit. Excuse me. What the fuck? Something completely weird happened right now. Just literally right now. The entire Chrome app just quit on its own. I've not seen this phenomenon before. I might have to check exactly what's going on. This is a bit weird for me. Okay, anyway. It's all fine. The stream did not close or anything. It's going fine. So I guess I'll be back to this. Yeah, I was about to look up exactly what Monkrus meant by it. Okay. Actually, I asked it something. Is there a topological category that considers path homotopy, as in the objects are points in the space and morphisms are homotopy classes of paths between them? Yes, this is a very standard and very classical construction in algebraic topology. Actually, two close related categories that you might be thinking of. The fundamental groupoid. This is the correct categories. Morphisms are homotopy classes of paths, and homotopy is taken rel endpoints. Okay, so these are homotopy relative endpoints. Okay, sure, why not? Fine. Well played. Definition. Let X be a topological space. The fundamental groupoid has objects points of X. and morphisms being pi 1 of x equal to path homotopy classes, relevant points, composition, concatenate paths, identities, constant paths, inverses, reverse paths. What is the right category? It's a groupoid. Every morphism is invertible. If x is path connected and you pick x0, then end of x0 is isomorphic to pi 1. If x is path connected, you need that. So the fundamental group appears at the endomorphism groups object in this category. This is exactly category of points and homotopy classes of paths. The path category, p of x, less common. Sometimes we will consider the raw path category, points of x and morphism being actual continuous paths. This is not actually one used in algebraic topology because it's far too big, not homotopy invariant, and there's no categorical nice structure. It shows up in categorical topology, higher category theory, and some approaches to directed topology, whatever those might be. Okay, whatever. So my current question. Moncrief is discussing changing base point of the fundamental group. Suppose x1, x0 and x1 are points in x, lie in the same path component. Pick a path from x0 to x1, then you get an isomorphism generated by that path, alpha hat, let's say, given by the conjugation of paths. The previous paragraph in Moncrief explains the different choices of alpha, let's say alpha versus beta, give in general different isomorphisms. What he means by path independent. Does the induced isomorphism depend on the chosen path alpha? So if you choose another path beta, do you get the same isomorphism? But the path connectedness means in plain path independence. Two base points and you want transports loops from to loops at x1, but the only way to do that is by a chosen path alpha that connects them. Different choices of the conjugation of the connecting path give in general different isomorphisms of fundamental groups. Path independence means the isomorphism does not depend on which path you choose from x to x0. This means geometrically core idea. Okay. Okay. Okay, so I should try and check, you know, a better way. So now I'm starting to question my first assertion that isomorphism of the fundamental groups is exactly the isomorphisms in the fundamental groupoid. Is that really true? Okay, I'll not use this guy for this one. I'll just try to do it myself. What is an isomorphism between these two fundamental groups? That is an isomorphism generated by paths, right? For any path P from x0 to x1 in the fundamental groupoid or not. Yeah, or not. F from I to x such that f of 0 is x0 and f of 1 is x1. This morphism exists in the fundamental groupoid. Why are there 25 trains going on in at the same time right now? Oh god, what is this symphony? Hold up a second. This is that moment. Yeah, it is that moment. So now the overture is coming. I guess we are exactly halfway through the Goldberg variations. This is number 16, right? Yeah, number 16. And what is this isomorphism F cap? Well, let's just entirely replace this by alpha. So this alpha cap on any F is given by this class alpha bar star F, or I'll actually use this my notation, alpha star F star alpha bar. So this map is from x1 to x1 in that case. Alpha bar is from x1 to x0. Alpha is from x0 to x1. So alpha bar goes from x1 to x1. Yeah, this is on x1. So this is the exact thing. So this is exactly this thing, right? That is exactly that conjugation, isn't it? Am I missing something very fundamental? Okay, anyway, so this is okay. Yeah, that is true. I might be, yeah, I might be missing something fundamental. So this statement is true. There is nothing wrong with that. So what I might be missing is that this there's only one isomorphism. That is not true. We're not saying that. Path independent. Path independent isomorphism between this. Okay, so basically if there's only one isomorphism, then it would be an instance of simple connectedness, right? Or simply connectedness, whatever. Anyway, so we say that for all alpha and beta, now we are talking about inside a fundamental groupoid itself, pi 1 of x of x0 and x1. We see that, you know, alpha p alpha inverse equals beta p beta inverse. Is that right? Yeah. For all p in, let's see, aught of x0, something like that. If this is the case, then let's do this. Beta inverse alpha p is equal to p beta inverse alpha. Now notice this one thing. Notice this one thing, that here is x0, here is x1, here is alpha, here is beta, here is alpha inverse, here is beta inverse, and let's see, here is p. Then beta inverse alpha p, then beta inverse p then alpha then beta inverse. So there is this thing right here, beta inverse alpha p. We say that is equal to alpha beta inverse then p. So that thing is equal to p beta inverse alpha. So now if pi 1 of x at x0 is abelian, well then indeed it is true that p, let's see what is this, beta inverse alpha p is equal to p beta inverse alpha. So that means alpha p alpha inverse equals beta p beta inverse for all alpha beta from x0 to x1, and for all p from x0 to x0. So we just showed one direction of the if and only if, namely the if direction, namely this direction. Now we have to show the other direction as well. Let's say these are not abelian. Okay, then we have to show that there exists some paths alpha beta such that this p does not this does not really work like that, right? Since this is non-abelian, okay, there exist two paths alpha and beta. Okay, we do it by contrapositive. If pi 1 of x comma x naught is, let's say, not abelian, that is to say that if the automorphism group aught of x naught is not abelian, then there are these two morphisms p and q from x naught to x naught such that pq is not equal to qp. Okay, p and q. Now consider this, let's see, I would take this I'll take this isomorphism this way, alpha. Consider alpha from x1 to x0. This is, of course, all of them are isomorphisms. You have to kind of have that alpha q is not equal to alpha, right? What happens? Okay, yeah. Note that p not equal to p and q, neither of these are equal to the identity morphism, right? Of course, because otherwise if one of them is the identity, then it of course commutes with the other. So it is not possible that p and q do not commute. So having chosen that, if it was the case that alpha q, let's say alpha q, right? No, it is q alpha. If it was the case that q alpha was equal to alpha, then you can just compose alpha bar first, right? So you can just compose alpha bar and get that q is equal to identity, which is of course a contradiction. So we get that q alpha is not equal to alpha, and q alpha are both isomorphisms from x1 to x0. Okay, so notice that we got ourselves two isomorphisms. I might even take three isomorphisms if I feel like I want it. So what we want is that we want to show that alpha inverse P alpha in alpha is not equal to Q alpha inverse P Q alpha. Right? We want to show that this is the case, because if it was that alpha inverse, am I doing this even in the right order? Yeah, I'm doing it right. Alpha inverse P alpha, if it was that this is equal to that, this says alpha inverse Q inverse P Q alpha inverse. You see what is going on? We compose with alpha on both sides, they cancel, you get P is equal to Q inverse P Q. This implies QP is PQ, which is of course the contradiction that we needed so far. So therefore, if the fundamental groups are not abelian, then it is true that there are basically distinct isomorphisms which do not depend on the path. So there's that. So we have shown this direction as well. And I guess we are done with this theorem as well. No? Yeah, looks fine. So far on the checklist, we have finished the checklist. In terms of checklist, I have no checklist. We are done with this part. What are we doing next then? I should go and fetch some water. I'm running out of water, kind of. This is 5:43, almost 6 a.m. I've got probably 1.5 hours in hand. Let's see. How long have we been going on for? This has been going on for 2 hours and 10 minutes. That's 2 hours 11 minutes. That's hell a long thing. And not a single soul on earth has been watching it. That's just so perfect. That's just so perfect. Why is everyone just posting videos about why they're quitting their PhDs? I don't want to know why you quit your damn PhD. You are just fucking incompetent. I'm very sleepy actually right now. I had 5 hours of time in hand. I might do the exercises of Monkrus for the sheer lack of a better thing to do. But I have better things to do. Might do the previous exercises and all that. I'm skipping all the exercises. That's a huge problem. Like, this will pile up like an enormous mountain on me, and I'll just die under that pressure. To have well, talking about dying under the pressure, that variation starts again. Okay, so the last thing I'll like to mention about this matter is a sort of hierarchy. First up, it is just any space, just any space. From that, we get a whole bunch of pointed spaces in top star. And applying the fundamental to that, we get pi 1 of x comma x in GFP. So there's that. Now, also you can get the fundamental groupoid first of all. So applying a bigger functor on this, and from that you somehow extract something interesting. So there is that commutative square. I'm just loving commutative squares. Commutative squares are just so great. I'm gonna say this to my friend. Okay. Now notice that if x is path connected, then, well, pi 1 of x has all objects isomorphic. Okay, so I was actually just mistaken here. The correspondence is not so direct. And the fact that this is not so direct exactly is the content of this theorem that I understood right now. All objects isomorphic. So pi 1 of x comma x naught is isomorphic to pi 1 of x comma x1 for all x naught and x1 in x. There's this one thing which is the kind of a next step in the hierarchy. After that step, you get something like if isomorphisms between pi 1 of x x naught and pi 1 of x x1 are independent of all these groups are abelian. And then so this basically says that if only one isomorphism from pi 1 of x comma x naught to pi 1 of x comma x1, then this is abelian. And you know, the abelian if and only if only one isomorphism between the two fundamental groups. Now what if there is exactly one isomorphism from x to x1? And that just means that pi 1 of x comma x are all trivial. So this is the most special, this is kind of the most special condition of them all. Simply connected space. What this, then I have to see what exactly this means. Okay, so there is. Oh, oh god, there is something more wrong going on. Okay. Uniqueness of base point change isomorphism if only 5 1 is a billion. Only one morphism in the groupoid, groups are trivial. In a fundamental groupoid, objects are points, and morphisms are homotopy classes of paths. Excuse me. An automorphism group acts translatively on the set of morphisms between two objects. The set might be singleton even if the group is non-trivial. Why is not the case? Excuse me, I do not understand. was about to get copy striked again. Is that composition in the wrong direction? Are you kidding me? What? What? Why? What? Bro. Hey, just wait up a second. Just wait up a second. This is why they tell us so many times to not use the goddamned ChatGPT. Yes, so I have to work it out myself. So look, my argument was that if there is only okay, wait, let me just finish the matter with this guy, then I'll show it in the stream. I've got a lot of time anyway. Are you kidding me? Are you what? 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 I mean, what is this going on? It claims since there is only one morphism, x1 to x0, we must have fq equal to q. This is wrong. Why? Because unique morphism between objects does not mean there is only one morphism with that codomain and codomain. In the groupoid, there is only one morphism up to homotopy. Are you kidding me? Why am I trading the OpenAI for free? Like, burning my time when it cannot. It's just so incompetent. It is just so incompetent. If is correct, yeah, after all. In a group of G, there is exactly one morphism P from, if there is exactly one morphism P from x0 to x1, then the automorphism group of x0 is trivial. Proof. Let P be the unique morphism and Q be the inverse, also unique. Fix any F in the automorphism. Consider the composite FQ, fuck you, which is a morphism F1 x1 to x0, but hom is a singleton which contains only Q. I compose both sides on the right with P. Compositions are defined, blah blah blah. So F is ID, so what is trivial. Same argument for Jesus Christ. Okay. So after like 5 messages, I'm getting to the right thing. So what was my original message? So what I understood is the one morphism between the fundamental group based to different points even only if the fundamental group is abelian. If there is exactly one morphism Base point change isomorphisms. Given a path x0 to x1, you get an isomorphism of groups. I mean, should I show this AI chat on the stream? I mean, there's no problem. There's supposedly no problem if I do, right? Bro, feral cats. Feral cats all over. Where's the cat, by the way? My brother in Animal Kingdom, where are you? There's somewhere I cannot see, really. Okay, if I cannot see it, then I don't bother. Yeah, let's just show this. Probably not this screen. Not this screen. Exactly which screen is going there? Wait a second. Wait a second. Excuse me. It's not window capture, right? It is window capture. Why is it capturing like... Oh, come on. Base point change isomorphism. adjacency functor. This is going into my collection of books right now. This will go there right now. Top GRPDS GRPD. Yeah. This is in my collection. This seems fun. Anyway, what else? We got Ronnie Brown right there. P.J. Higgins, Notes on Categories and Groupoids. Mackenzie, Lie Groupoids and Lie Algebroids. Saunders MacLean, Categories for Working Mathematician. I mean, that book is everywhere. I should probably get a copy of that book. I should probably get a copy of MacLean. Yeah, that sounds like something worth it. Classical topology text, J.P. May, Spanier, Hatcher. Footnotes but minimal. Hatcher would not give this much beautiful machinery. I love this variation. Anyway, so that is there. What are we doing after this? So there was some stuff right there. Basically this hierarchy. Moving on from this is let's see. Still need the lamp somehow. There's not enough light from outside that's coming. So, okay, I'll just have a brief look at the induced homomorphism things, because it is just the functor. So So it is just the basically pion functor from top star to GRP. So what this does is that if there is a continuous map, let's say f from base point preserving map x from x comma x naught to y comma y naught, then there is a an induced homomorphism. Then there's an induced homomorphism f star from x to x naught, from x comma x naught to y comma y naught. Well, not really those. Pi one of these, the fundamental groups. Okay, that is the induced homomorphism. I don't know what to even say because it's also trivial. Okay. Yeah, it is all just super trivial stuff. Okay, let's see, what is this homomorphism? If H is a basically a let's see, F star, this homomorphism applied on H star gives this thing, which is this group of star F. Or is that even true? No, it is not true. It is F composed with H. Yeah, so H is a map from I to X, F is a map from X to Y, so F composed with H is a map from I to Y, such that F composed with H of 0 is Y naught, also the same as F composed with H of 1. Okay, so that is the homomorphism. F star of, let's do this one, H and G equals, let's see, F star of, H star G here equals F composed with H star G and that is exactly fh star fg, so that is equal to f star of h f star of g. I mean, exactly, this is a functor, right? So a functor behaves like a functor. You cannot, come on, yeah, what do you expect? It is a functor from top star to group. It behaves like a functor from top star to group. Okay. So looks like we have come to the end of the section in Monkrus. After this is exercises and then covering spaces. I'll probably spend today. Actually, I won't get time to do covering spaces today because I'll have to do some tilings. Got some presentation in the tilings next Tuesday. So yeah, that is do the tilings. Homotopy fundamental group. Yeah, enough of that. Let's look at what Hatcher has to say, and maybe after that I'll just shut this stream and go to not probably sleep, because if I sleep right now then my tomorrow is completely done. Like my today is completely finished if I sleep now. Change of base point, just that. Change of base point map is an isomorphism. If there's a path connected, then up to isomorphism. Independent of the choice of base point. Yeah, sure, why not? I saw something written somewhere. I mean, this cannot be just fluke or anything. Oh yeah, it was in this section, I think. Or not really. Where was that? Is a homotopy equivalence and then induced homotopy. Okay, yeah, that's a great one. So we might actually look at this. Yeah, we might look at this. Base point preserving maps. Okay, yeah, we might deal a bit more with the various topological spaces and functors between them. I guess I'll be back soon. I just want to go and get some, you know, I want to go and get some fresh air. So, yeah, until we meet again. I'm not ending the stream, I'm just taking a break for like 5 minutes. Yeah, so I'll be back. Yes, we are back. I was just having a look at the list of all topological categories, which seems to include things like, let's say, things like top, things like top star, H top, or sometimes also called hotop, uh, H top star. I'll just give a brief rundown of what these things are. I mean, okay, first up, top. Everyone knows what top is, right? Top is the category. Oh, I wrote it so bad. Category of topological spaces. So objects are topological spaces. It's funny how I used to write topological spaces like this before. So you have the set X and the topology T. That is how I used to write topological spaces. Now I just write X and write base point topological spaces like this. So, like, yeah, it's slightly weird. Morphisms are continuous maps. Okay. Composition, ordinary composition functions. Identity, the identity map for its space. Categorical properties of top has limits and co-limits, but some are too large. That is, function spaces don't lie in top unless topology is modified. Okay. Not Cartesian closed. The exponential object does not exist in general. Okay. Subcategories matter. Hausdorff, locally compact, compact Hausdorff, K-spaces are all meaningful subcategories. Top pointed spaces. Star. So, okay. Up next is about top star. Okay, I wrote this top part in a very poor manner. Pardon my handwriting. I'm trying to improve, especially at least for the tab and pen system. So it is the category of pointed spaces objects are these. X is where X is in top now, and actually I can write this in a better way. X naught is in X is in top. Continuous maps f from x to y such that f of x naught equals y naught. So the maps must preserve the base points. This is a smash product making top closed symmetric monoidal category. Closed symmetric monoidal category. So it's talking about stable homotopy theory and all that. Okay, anyway, we'll come back to those things a bit later. Let's talk about H-top. Homotopy category. This is obtained by identifying maps that are homotopic. Okay. Yeah, sure. So we only take the maps up to homotopy for H-top. The objects are the same as in top. Morphisms are, let's see, morphisms are homotopy classes of maps. Let's put it like this. I would like to write it like this. Hom sub H-top of x comma y is equal to hom sub top of x comma y quotiented by homotopy with homotopy of maps. Recall homotopy of maps, that was there. So this is exactly the definition. Okay, we can get some more stuff done. Homotopy class of IDX, composition, blah blah blah. Homotopy equivalences of some actual isomorphisms. Homotopy equivalences become actual isomorphisms. Yeah, that is true here. Isomorphisms are exactly the homotopy equivalences instead of homeomorphisms. So yeah, in top, the isomorphisms are homeomorphisms. In top star, isomorphisms are base point preserving homeomorphism. And in H-top, isomorphisms are exactly homotopy equivalences. Recall that a homotopy equivalence f from x to y is such that there is g from y to x such that gf is homotopic to identity on x and fg is homotopic to identity on y. So that is what exactly homotopy equivalences are. So look at this. When we say f is homotopic to g, this is going on in top. Then immediately we do that quotient by homotopy. We see that the class of f is equal to the class of g in h top. So that is the power of a quotient, that you got x equivalent to y in, let's say, x, and you take the quotient, you get that the class of x is equal to the class of y, and x quotient is equivalence. Isn't that so beautiful? H top star. Homotopy classes are base point preserving maps. Homotopies are also required to fix base points. So yeah, that's true. Okay, that was H top. Up next is H top star. What do you mean by pointed homotopy spaces? That makes no sense. Spaces with classes of base point preserving homotopies. Okay, that was my alarm. I guess I should turn off the alarms. So there's that. Okay, this has been going on for quite a long time now, and okay, 3 hours and 30 minutes. I was supposed to be streaming for like at least 5 hours, not at least 5 hours. I thought I'll be going on for 5 hours, but I'm feeling quite tired actually, and I guess that is natural after sitting in a chair and going up like 3 times in 3.5 hours. So I might close the stream, and until then I just have a look at exactly what we have done so far. It is not very much. It is very, very little. We started here, did all this little stuff, and then spent like at least 20 minutes over this, arguing with a clanker. Then look at this functor for a second. Then I took a long break once again, and then look at these categories, topological categories. Maybe these one for now. There could be topological groupoids, which we cover at some point, but okay, maybe not now. We can have that later on as well. So I guess I would close the stream. Or maybe just I'll go silent and do my stuff while the stream runs like a stream. Okay, there's a chance to end the stream at 3:33 at 33, so I'll do that. Yep, exactly end now. It went on for 35. Okay.